Hello students, in this video lecture I am going to discuss the concept of lattice and complete lattice. Now before I discuss the concept of lattice and complete lattice, I would like to recall these two notations, the notation of V and inverted V. Now this notation which is V, which we call as join, and this notation which is inverted V, which we call as meet, these are two operations, the join operation and the meet operation, which we have already discussed in separate videos, and examples also have been taken up for calculating the join of two elements, or if you are in a PO set, P less than equal to, it was discussed in detail how to calculate join of two elements provided it exists, how to calculate meet of two elements provided it exists, where X and Y are elements in the PO set P. Also, if S is any subset of P, how to find out the join of S, how to find out the meet of S. This has been discussed already in my earlier videos along with the many examples. So if one is interested in knowing more about these operations of join and meet, we can go back to those videos, but for the sake of understanding what we mean by a lattice and what we mean by a complete lattice, let me just briefly recall these operations, the join operation and the meet operation in a PO set P. So let us suppose that P less than equal to is a non-empty partially ordered set or a PO set. Then let us understand what do we mean by this operation, the join operation. This operation V, which is denoted by V, is called the join operation. Now if you pick up any two elements X and Y belonging to P, then X join Y is the supremum of X and Y, or this is the least upper bound of X and Y, provided the supremum of X and Y or least upper bound of X and Y exists. So least upper bound of X and Y means that least upper bound of X and Y is that upper bound of X and Y which is the least. So if this least upper bound of X and Y exists or supremum of X and Y exists, then it is called the join of X and Y, and this is the notation that you use for join of X and Y. So this was one thing that was discussed in detail in my earlier videos. Then coming to what do we mean by this particular notation, the inverted V, which is read as the meet operation. Again, if you have X and Y are any two elements of P, the partially ordered set P, then X meet Y, this stands for the infimum of X and Y provided it exists, or this stands for the greatest lower bound of X and Y provided it exists. Greatest lower bound of X and Y means that lower bound of X and Y which is the greatest. So if these two things exist, if these two things exist, the least upper bound and the greatest lower bound of X and Y, then we say that the join of X and Y exists and the meet of X and Y exists. So this was something which was discussed earlier. Again, if you have S to be any subset of P, then you can always talk of join of S, and you can talk of meet of S provided they exist, where join of S would mean join of the elements of S, whatever elements S has, and the meet of S would mean meet of elements of S, or the greatest lower bound of elements of S. This would be the least upper bound of elements of S, and this would be the greatest lower bound of elements of S, provided these two, which is the least upper bound of S and the greatest lower bound of S, exist. If these two are existing, if least upper bound of S exists, we say that Vs exists, or the join of S exists. If greatest lower bound of S exists, then we say that the inverted Vs exists, or the meet of S exists. So these four things were discussed in details along with examples earlier, but once we are familiar with these notations, now let us try to understand what do we mean by a lattice and a complete lattice. Now again, for the definition of a lattice and a complete lattice, suppose you are in a non-empty PO set P less than equal to, the definition of the PO set or a partially ordered set has already been again given. So those basic definitions, we are assuming that we know them, and in case one is not familiar with the definition of a partially ordered set or a PO set, you can always refer to those videos that have been made regarding partially ordered sets, where PO sets have been discussed in detail. Now suppose you have P less than equal to is a non-empty partially ordered set, where less than equal to is the PO relation. Now when is this set said to be a lattice? The set P less than equal to is said to be a lattice if whatever pair of elements x and y you choose from the set P, from the PO set P, x join y and x meet y, which is x join y means the supremum of x and y, and x meet y means the infimum of x and y. These two always exist, and this means that whatever pair of elements x and y belonging to P you may choose this. This means that for every pair of elements x and y belonging to P that you take, x join y, if this always exists, and x meet y, if these two things always exist, and if this happens for every pair of elements in the PO set P, then the PO set P is said to be a lattice. So this is one definition that we have, which I had to discuss in this video. Examples, of course, we'll be taking. Then now the next question is that when is this PO set P less than equal to, the non-empty PO set P less than equal to, said to be a complete lattice? Now this this PO set P is said to be a complete lattice if whatever subset S of P you may take, the join of S and the meet of S, if these two things always exist, then, and if this happens for every subset S of P, then you say that the PO set P is a complete lattice. So these are two simple definitions of lattice and complete lattice. When you are talking of lattice, then you take a pair of elements, and for this for any pair of elements that you take, the join and the meet should always exist for a PO set to be a lattice. And when you are talking of complete lattice, then you take any subset S of P, and for any subset S of P that you take, the join of S and the meet of S should always exist for the PO set to be a complete lattice. So now with these simple definitions, let us come to a few examples to understand the concepts better. Now, so let me start with the first example. Now let us take the PO set which is a chain of 4 elements. Now a PO set which is a chain of 4 elements has hash diagram which looks like this, and just to refer to these 4 elements, I am giving some names to them. Let me call these 4 elements as A, B, C, D. So this PO set P is 4. 4 means it's a chain of 4 elements. And now let us try to find out whether this PO set is a lattice or not. Just randomly pick any pair of elements A and B, and just find out the join of A and B. Now the join of A and B is the element which is acting like a least upper bound for A and B, and which is of course B. I have discussed this in my earlier videos. The element which is above both A and B, that will be just above both A and B, that will be the least upper bound of A and B, or the join of A and B. And what is the meet of A and B? That element of the PO set P which is just below both A and B, that will be the meet. So this is A. So the join of A and B is B, and the meet of A and B is A, which means it is existing. Let me calculate the join of A and C. The element which is just above both A and C is C, and the element which is just below both A and C is A. So the join and the meet of A and C is also existing. Likewise, you can pick up any pair of elements in the chain 4, and you can show that the join of for any element x and y, for any pair of elements x and y that you choose in P is 4, which is the chain of 4 elements, you will see that join of x will always exist, and join of x and y will always exist, and the meet of x and y will always exist, which means that the given PO set P, which is a chain of 4 elements, is a lattice. In fact, here we have precisely taken P to be a chain of 4 elements, but it is the number of elements is not important in this chain. You can have instead of 4 elements, I could have taken 5 elements in the chain, or I could have taken P to be equal to 6 elements, which means a chain of 6 elements, or a chain of 7 elements. In all the cases, the argument remains the same, that if you pick up any pair of elements x and y belonging to P, they will always have a join and they will always have a meet, which means that because they always have a join and they always have a meet, because join of x and y will always exist and meet of x and y will always exist, which means that these chains, the chain of 4 elements, the chain of 5 elements, the chain of 6 elements, the chain of 7 elements, all these are lattices. Now we try to find out whether these chains, particularly concentrating on the chain of 4 elements, we want to find out whether this chain of 4 elements whose hash diagram is given by whether this is a complete lattice or not. So what we do is pick up any arbitrary subset S of P. Let's say just for the sake of illustrating whether this P is a complete lattice or not, I'm just taking any arbitrary subset S of P. Let's say I'm taking A, B, C. That is, I'm taking this particular subset of the chain 4, which is consisting of these 3 elements, and I try to find out whether the join of S and the meet of S exists or not. Now the join of S will be that element which is such that element of the PO set P which is such that all the 3 elements of S are smaller than that, and that particular element is C, because C is that element of the PO set P which is such that all the 3 elements A, B and C are smaller than it. In fact, C is not the only element which is such that all the 3 elements A, B and C are lesser than C. D is also one such element such that all the 3 elements A, B and C are lesser than D. So C and D both are acting like upper bounds for the set S, which is A, B, C, because C is greater than all the 3 elements A, B and C, and D is also greater than all the 3 elements A, B and C. So C and D are both upper bounds of the set S, but out of the 2, C and D, the one which is the least upper bound is C. So C is the least upper bound of these 3 elements A, B and C, or C is the supremum of S, or C is the join of S. So the join of S is C. Again, by the same argument, a similar argument, if we try to find out the meet of S, the meet of S is the infimum of S, or the greatest lower bound of S. Then the greatest lower bound of S will of course be A, because A is that element of the PO set P which is smaller than all the 3 elements. So A is a lower bound of S, because A is smaller than all the 3 elements A, B and C, and also A is the only lower bound of S. There is no other element which is behaving like A, because there is no other element which is at a lower level than A, so or which is lower than all the 3 elements A, B and C. So A is the only lower bound of these 3 elements, so that way A becomes the greatest lower bound, or it becomes the infimum of S, or it becomes the meet of S. So this means that the join of S, the meet of S, both exists, and likewise you can verify whatever subset S of P you may choose, you will always be able to find the join of S and the meet of S. In particular, if you regard P as a subset of itself, this is the set P, and every set can be regarded as a subset of itself, and if we try to find out what is the join of P and what is the meet of P, then join of P will be that element which is such that all the elements of P are lesser than it. So join of P, which should be an upper bound, so which means all the elements of P should be smaller than it, they should be lesser than it, and we see that D is that element which is behaving in such a way that all the elements, all the 4 elements A, B, C, D are smaller than it, and D is the only so that way D is a upper bound, and D is the only upper bound that P has, so that way this is the least upper bound. Again, so join of S, so join of P, this means exists, and also we note that D is the top element. The top element is generally denoted by capital T, so the top element T is existing in this chain, and that is D, and that top element is acting like the join of P. And if we try to find out what is the meet of P is that element which is smaller than every element of P, and that element which is smaller than every element of P is A, and so that way A is a lower bound, and because A is the only lower bound that we have for this particular chain P. So this A acts as the greatest lower bound or the infimum, greatest lower bound of P, or the infimum of P, or the meet of P. So the meet of P is existing, and that is A. And again we can see that A is the bottom element. The bottom element is generally denoted by the inverted T. So we can see that the top element which is existing in this PO set P, which is a chain of 4 elements, is acting like the join of P, and this bottom element which is existing in this particular chain of 4 elements is acting like the meet of P. And also we have seen that for every subset of S, you can verify in fact this fact, that for every subset S of P that you take, you will always be able to find the join of S. And you will be able to find the meet of S. This will always exist, which tells me that this particular chain of 4 elements is a complete lattice, because every subset has a join and a meet. And in fact, as we have seen that the join of the this PO set P is the topmost element, which is D, and the meet of the PO set P, which is the bottommost element, which is A. So here we have, in this particular example, we have taken P to be a chain of 4 elements, but then the same argument goes for a chain of 5 elements, 6 elements, 7 elements. All these chains are not only lattices, but they are complete lattices. So that was example 1, and now coming to example 2. Now in example 2, we take the example of power set of a set, where power set of a set is the set of all subsets of that set. So let me take X to be any set consisting of, let's say, 3 elements, 1, 2, 3, and the power set of X, which is the set of all subsets of X, in that case, because X consists of 3 elements, so the power set of X consists of 2 to the power 3, which is 8 elements, and those 8 elements of power set of X are given by the empty set phi or the null set, then singletons, that is sets consisting of just a single element or one element, and then sets consisting of 2 elements each, which means that 1 2, 1 3 and 2 3, and the set X itself. So these are the 8 elements of power set of X. And we have already seen that the power set of X with respect to the inclusion relation, or with respect to the relation is contained in or is subset of this particular set, is a PO set. So that has been discussed in detail in my earlier videos. Now again also we know that the hash diagram of power set of X can be expressed in the form of cube, which again was discussed in details in my earlier videos. So this is how the hash diagram of power set of X looks, where at the top we have the element X, which is the whole set X, which is the set 1 2 3, the underlying set 1 2 3, and at the bottom we have the empty set or the null set phi, and then at the level above, just above phi, we have the singletons 1 2 and 3, and then at the above level, the level above then singletons, we have the sets consisting of 2 elements each, that is here we have 1 2, and at this point we have 1 3, and at the last level, this is the set 1 3, and at this last element is the set 2 3. This is what we have. And now when we know that this is the hash diagram for power set of X, then using this diagram we can find out the join and the meet of various elements. Now but the question here is that this particular set, which is a PO set, we have to find out whether it is a lattice or not, or whether this is a complete lattice or not. Now as far as the power set of X is concerned, then this particular set where the PO relation is the inclusion relation, this particular set is not only a PO set, but it is a lattice, and also it comes out to be a complete lattice. Now this can be, these two facts can be verified by using the hash diagram of the power set of X. Now for showing that the power set of X with respect to the inclusion relation, this is a lattice, we can pick up any pair of elements X and Y belonging to the power set of X, and we can verify that whatever pair of elements X and Y we choose from the power set of X, the join of X and Y and the meet of X and Y both will be elements of power set of X. So for example, if we take let's say the elements 1 and 2 belonging to the power set of X, we can note that these two elements, from the hash diagram itself we can see that the join of join of 1 with 2 is the element which is just at the top of 1 and 2, the element which is greater than equal to both of them, and this is 1 2. So because this is this particular set 1 2 is not only an upper bound of singleton 1 and singleton 2, but it is the least of all upper bounds. There are in fact two upper bounds for these two singletons. There are two upper bounds that we have. One is this element 1 2 and the other is the set X itself, but the least of these two upper bounds is the set 1 2. So the join of singleton 1 and singleton 2 is 1 2, and if we try to find out the meet of 1 and 2, then the meet of 1 and 2 is that element which is acting like a lower bound, and it is the greatest of all lower bounds, and the lower bound of 1 and 2 is the empty set and or the null set, and this is the only lower bound of 1 and 2. So that way this is the greatest lower bound. So likewise we can pick up any pair of elements X and Y belonging to the power set of X, and we can verify this fact that the join of X and Y and the meet of X and Y, both these two will be elements of power set of X. Both will exist and they will be elements of power set of X, which tells me that the power set of X with respect to the inclusion relation is not only a PO set, but it is also a lattice. And then coming to the second point, that how this power set of X with respect to inclusion relation is a complete lattice. Again we can verify that for any subset S of P that we may take, the join of S and the meet of S will always exist, and they will be elements of power set of X. For example, if we take let's say S to be the set consisting of three elements, let's say the element 1 and the element 2 and the element, let's say X, which is the whole set, then in that case we can just see that the join of S, which is the element which is greater than equal to all three of them, will be X itself, and the meet of S, which is the element which is less than equal to all the elements, and will be phi. So this means that the join of S and the meet of S exists for this particular set S. And then again if we take S to be the set let's say 1, the set consisting of 1 and 1 2, and let's say the set X, then again we can verify that the join of S, which is the upper bound, the least upper bound of the three elements of S, is that element which is greater than equal to all the three elements of S, and that is X, and the meet of S, which is the greatest lower bound of the elements of S, which is, and that is the set, that is the element 1. So in this case also the join of S and the meet of S exists. So likewise we can see that whatever subset S of P that of the power set of X that we may choose, the join of S and the meet of S will always exist, and they will be elements of the power set of X. So that way the power set of X comes out to be not only the lattice, but it also comes out to be a complete lattice. So that was all about lattice and complete lattice.